Hey guys, Christian here. We've got a weird, full-on, kind of hectic polynomial at the moment when we're asked to sketch the graph. So this has got a power of 4, power of 3, no power at all, power of 2, power of 5. So what's that? 4, 7, 8, 10, power of 15. So a polynomial of the 15th degree, and we're asked to sketch it. It sounds a little wild, but because this polynomial is already in factorized form, it's actually really, really easy. All we have to do is use all the skills that we have to find the x and y intercepts, and the rest comes really naturally. So we're going to have a look first at the x-intercepts. So if we have a think about these x-intercepts that we're trying to find, imagine if you made y equals 0. You'd have 0 equals, and then all of the factors, right? So x plus 5 to the power of 4, x plus 2 to the power of 3, x plus 1, x minus 2 to the power of 2, and x minus 4 to the power of 5. You can use, because this polynomial is factorized, you can use the null factor law on each individual piece. So we're actually going to have 5 different x-intercepts, one for each set of brackets, and each of them will behave a little bit differently. So that first one, we basically have x plus 5 equals 0, therefore x equals negative 5. But what's important about this is the fact that because that factor has a power of 4, this intercept will actually be a turning point. Alright, so it'll be an actual turning point. It won't go through negative 5, it will touch negative 5 and then come back either down or up depending on which way the graph is going. So what we can do is we can use that same logic for pretty much all of these. We would find for the second factor that x equals negative 2, and because that's an odd power, that would be a point of inflection, which is one of those ones where it goes, up, flat, up. Going through and doing the rest of the factors, we'd have x minus 1, x equals minus 1, sorry, which would be linear, because there's no power. We'd have x equals 2, which will be a turning point, and we have x equals 4, which, because we've got a power of 5, will be another point of inflection. So when you're dealing with polynomials like this and you've got factors to various powers, long story short, no power will be linear, so go straight through that intercept. Any even power will be a turning point, and any odd power will be a point of inflection. That's just the way it works, which actually makes life really, really easy. So we could almost sketch a reasonable assumption of this graph now, but let's take it one step further. We'll quickly find the y-intercept as well. Now the y-intercept comes from making x equals 0. So what we would have here is we have y equals, and we'd have 0 plus 5 to the power of 4. So that's just 5 to the power of 4 times 2 to the power of 3 times 1 times negative 2 to the power of 2, and then times negative 4 to the power of 5. So you're definitely going to need your calculator to go through this, but it's actually not as bad as you might think. Realistically, if you weren't given access to the calculator, the question would not be this hard. So we'll jump on our calculator, we'll go 5 to the power of 4 times 2 to the power of 3 times 1 times negative 2 to the power of 2, and then times negative 4 to the power of 5. And we come up with a really, really big number, but that's okay because we just have to factor that into our graph, and we don't have to draw everything perfectly to scale. So we've got our y-intercept. Oh, sorry, it's negative. It's ugly, but we can graph it. We actually have everything we need now, so we can draw up a quick little sketch. All we have to do is mark out all of the intercepts and then graph them accordingly. So let's mark out 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'd fully expect that when you're doing this, use a ruler to get it a little bit neater than mine. But we can now go through and actually graph what we're going. So I've got an intercept at negative 5, which is a turning point. Point of inflection at negative 2, linear at negative 1, turning point at 2, and point of inflection at 4. The only problem is we don't know where to start. Now with any polynomial when you're graphing, it's actually easier to think about where you finish. Because in very simple terms, any polynomial, if it's a positive polynomial overall, it will finish by going up. And if it's a negative polynomial overall, it will finish by going down. So this is a positive polynomial, and I know that because if I multiplied all the x terms together, including their powers, we would end up with a positive value for the largest x term, so the largest powered x term. So we know that this is a positive polynomial, it's going to finish by going up away from the x-axis. So because our intercept the furthest to the right is our x equals 4, I'm actually going to work backwards from the right-hand side to the left-hand side because it's easier to manage. So we know that it's going to finish by going up, and it's going to get to x equals 4, and that's going to be a point of inflection. So we're going to start with something like this. All right, you can see it sort of takes that little flat spot right in between and then keeps going. The next intercept is where x equals 2, and that is a turning point. So it's actually going to come back up for 2 and then come back down because it's a turning point. When x equals -1, it's a linear factor, and we do know that it shoots a long way down to get to its y-intercept before coming back up and going straight through -1. It then comes back down for -2 and gives us a point of inflection. And finally, it comes back up for -5 and gives us a turning point. So this is a fairly reasonable representation of what the graph would look like. Just make sure, obviously, you label all of your information correctly so that you've got all of your details. You'd probably want to put coordinates in for the actual intercepts. And you want to make sure that you label your y-intercept as well. But once you've done all that, you can actually see that if you use this manner, you could graph literally any polynomial if it's been factorized. You can follow the same method no matter how simple or complex a polynomial is, as long as it's been factorized, because when it's been factorized, you can use this method to find your x-intercepts, smash through and find your y-intercept, figure out whether it finishes by going up or down, and from there, you're good to go. So if you like this video, like always, make sure you like it, share it with your friends, all that kind of stuff, and I will see you on the next video.